Okay, so any doubt from the last class? Afroza, Jubaina? Okay. So up to last class, we have completed capacitors and the circuits of resistor as well. Now let's start with chapter number 3. That's current electricity. 3, which is current electricity. So let's start with the introduction of electric current. So up to chapter number 2, we have electric charge at rest. We have studied all aspects of charge if it is at rest. All aspects of electric charge until that charge is at rest. Like if a charge is at rest, it can exert force. If a charge is at rest, it can generate electric field. Charge at rest can have potential energy. Charge at rest can generate potential. So all aspects related to a static charge have been studied up to chapter number 2. From chapter number 3 onwards, we will study motion of charge. We'll study the aspects of the charge in motion. So current is flow of charge. It's flow of charge. So if a charge is at rest, so if your charge is at rest, charge at rest generate electric field, potential energy, and obviously force. So these are aspects which are related to the charge at rest. But if the same charge comes in motion, charge in motion constitute current. So if a charge is in motion, it will generate current. So current is simply the flow of charge. The charge in motion constitute current. So current is nothing but the flow of charge. So if you have an electron at rest, there is no current. But if this electron starts moving, then you would say there is a current flowing in some opposite direction. That's it. If you have a proton at rest, no current. If this proton starts moving, then in the direction of motion of proton, you have current. So current is just the motion of charge. If your charge is at rest, it's electrostatic. It's a source of electric field, potential energy, electrostatic force. But if the same charge comes in motion, it's a source of current. So now we will see what will happen if charge starts moving. Just note it down. They will start with formally with electric current. So can I raise it? Can I raise it? Electric current. So electric current is simply the rate of flow of charge. So electric current, it is the rate of flow of charge. The rate of flow of charge is known as electric current. Say, let's consider a conductor. So you have a cylindrical conductor. Charge delta Q flows through this conductor in time delta T. A charge delta Q will flow through this conductor in time delta T. So charge delta Q flows through cross section in time delta T. So this is the charge that's flowing through the conductor in time delta T. So current is I, which is the ratio of charge in time. So current is simply the ratio of delta Q and delta T. This is your current. Ratio of charge in time is called. Now this current is your average current. You can as well calculate instantaneous current. For instantaneous current, you just shrink the time interval. Just shrink this time interval delta T. For instantaneous current, take limit delta T tends to 0, it's delta Q over delta T. This delta Q over delta T would be its dQ over dt. So that is your instantaneous current, which is dQ over. So average is charge divided by time. Instantaneous is just derivative of charge with respect to time. So current is a tensor quantity. It's neither a scalar nor a vector. But for all practical purpose, we will consider current as a scalar. So I'm not writing tensor. I'm writing it as a scalar. Basically, scalar is a category of tensor. Its SI unit is ampere. Ampere is the SI unit of current, the SI unit ampere. Next, see direction of current. Direction of current. So for direction, you can consider direction in two ways. You have two types of currents basically. One is conventional current and another one is electronic current. The first one is conventional current. The direction of conventional current is same as that of motion of positive charge. Its direction is same as that of motion of positive charge. Motion of positive charge. Or opposite to that of motion of negative charge. Or opposite to that of motion of negative charge. So this is the direction of current basically, same as that of motion of positive charge and opposite to that of motion of negative charge. Means if you have a positive charge, it's moving in this direction with a velocity v, then this is the direction of current. But the same negative charge is moving in this direction with a velocity v, then the direction of current would be opposite. So this is about the conventional current. Okay, note it down and tell me if you have any doubt. Just note it down and tell me if you have any doubt.
Sir,
Yes, Rivana.
so for instantaneous current, it's like I equal to dq by dt, right?
Yeah. That's differentiation of
So that dq is delta. Okay.
its derivative of charge with respect to time. You're differentiating charge with respect to time. But for average, you are dividing charge with time.
Okay. So for instantaneous, we had to use the derivative formulas and all.
Yes. For instantaneous, you have
Okay.
to use the derivative. So can I raise it? So can I raise it? Okay, so I'm erasing it. Next is after conventional current, the next type of current is electronic current. After conventional, the next type of current is electronic current. Its direction is opposite to that of charge. Direction is opposite, or sorry, not opposite, is same as that of motion of negative charge. Motion of negative charge. So this is the conventional current. Its direction is exactly same as that of motion of negative charge. So if you have a negative charge and it's moving in this direction with a velocity, then your current too will move in the same direction. But throughout this chapter, current electricity, we will always deal with conventional current. By default, current means conventional current, always. You can even consider the direction of conventional current using the cell. In a circuit, direction of conventional current is from high to lower potential. High to lower potential. So this is the direction of conventional current. The direction is from high to lower potential. That's conventional current. So if I give you a circuit, this resistor R, then the direction of current is from positive terminal to the negative terminal. This is the direction of conventional current from high to lower potential always. Okay, just note it down, then we'll do the next topic. Fatma, conventional current simply means current that flows due to motion of positive charge. That's conventional. Simply, which flows due to motion of positive charge. That's conventional. And if we start taking electron for conventional current, then we write that current which is flowing opposite to the motion of flow of electron is conventional. This electronic is due to motion of electron. Okay, so can I erase it? Okay, let's start with few problems. Charge flowing through a circuit is Let's say this is the equation of charge, 3t square plus 2t plus 1 coulomb. This is the charge which is flowing through a circuit. Calculate current first in 0 to 2 seconds, at t equal to 2 seconds. Okay, Fatma. So in 0 to 2 seconds, what does it mean? Is it average or instantaneous? Asking from 0 to 2 seconds, what does he mean? He's asking to calculate average. Yes. Whenever you have interval means the current that you are supposed to calculate is average. And what about the second term? It's an instant, no interval. It's asking you to calculate current exactly at 2 seconds, which would means that this is instantaneous. Instantaneous current. Solution. So this is charge with this 3t square plus 2t plus 1. So when I say average current, that is delta Q over delta T. Delta Q means Q2 minus Q1. Delta T means T2 minus T1. This is charge divided by time interval. If I write that T1 is equal to 0, the initial instant is 0. Then Q1. Afroza, what would be Q1? Charge at t equal to 0. How do you calculate charge at t equal to 0? Afroza. No answer. Fatma, how do you calculate charge at t equal to 0?
Place 0 instead of t.
Yes. Instead of t, just substitute 0. So that's 3 into 0 square. 2 into 0 plus 1. So your Q1 is 1 coulomb. The next T2, it's 2 seconds. So put t equal to 2 here. So it's 3 into 2 square plus 2 into 2 plus 1. So your Q2 is, it's 4, 3, 12, 12, 4, 16, 1, 17, it's 17. I just substitute the values here. So it's 17 minus 1 by 2 minus 0. It's 16 over 2, which is 8 ampere. No issue, Afroza. So that's 8 ampere. Second part. So for instantaneous current, you need to differentiate charge with respect to time. Instantaneous is dq over dt. So that's simply d over dt of q. D over dt of q means your q is 3t square plus 2t plus 1. If I differentiate it, this 3 is constant. You can take this 3 outside. Just differentiate t square. So the derivative of t square is 2t to the power 2 minus 1 plus 2. You can differentiate t to the power 1. Its derivative is 1. It's 1. If you differentiate 1, it's 0. 60 plus 2. So it's t equal to 2 seconds. If I substitute t equal to 2 here, then it's 6 into 2 plus 2, 12 plus 2, that's 14 meter. 49. So is it clear? Everyone?
Yes, sir, it's clear.
Okay, just note it down. We'll do one more numerical on the same concept. Just one more numerical on the same concept. So, can I raise it? Yes. This numerical is a bit tricky. Like instead of usual equation, I am giving you the graph between current and time. This is 5 seconds. This is 10 seconds. This is time in seconds, current in ampere. This is 5. Find the amount of charge that flows through the time, that flows through the wire calculate that flows through the wire and average current. So you have given current versus time graph. Using this current versus time graph, you're supposed to calculate charge. See, remember this small trick for graphs. It will be very useful. You have current is charge upon time. Charge is current multiplied by time. So if you get a quantity by the multiplication of two quantities, like charge is the product of current and time. And if graph is given between current and time, then the area between these graph will give charge. If Q is equal to the product of two quantities, then the area between the graph will give the third quantity. So here charge is current multiplied by time. So area under current versus time graph will give charge. So it's always like, if I write that V is equal to IR, voltage is current into resistance. Fatma, if current versus resistance graph is given, how would you calculate voltage from that graph?
By area under graph.
Area under graph. So whenever you have product of two functions, then the area under the graph of those two functions will give third quantity. So here area under the graph is charge. Area, or I should write this as, it's not I, delta. Your I is delta Q over delta T. So your delta Q is I delta T. So charge is area under the graph. Area under the graph. Okay, if I mark these points, let's say I call this as A, I call this point as B, I call this as C, this as D, and this as point E. So Froza, what shape is this? This A, B, C, D, E. What shape is this? Froza.
Quadrilateral.
Any particular shape? Because quadrilateral would be square, triangle, everything is quadrilateral. Any particular shape?
AB and E is triangle,
Okay.
and then EBCD is rectangle, square.
Right. Can I say that A, B, C, D, E is a trapezium? It's a trapezium. It has some two parallel sides. Yes, Yes, you can divide this in terms of triangle as well as square. Both the methods are correct. Or so you can simply write this as area of trapezium. A, B, C, D, E. Does anyone remember the formula of area for a trapezium? Formula for area of trapezium. No one. It's half, not half B into H. It's half sum of parallel sides. The parallel sides are AC and ED multiplied by the separation between them. Separation between them is DC. So your delta Q is half. Okay. You can even break your trapezium in terms of triangle and rectangle if you want. So that's half AC. How much is AC? It's 10. Plus ED, 5 to 10. This much of length, that's 5, right? It's 5. Multiplied by DC. This is DC. DC is again equal to 5. So delta Q is, it's 15 into 5 by 2. 75 by 2. Or you can write that your 75 by 2 is 35, 32, 32.5. 32.5. So average current is delta Q over delta T. So that's 32.5 divided by time. So the total time is 10 seconds. So that's the answer of first part. So your I average comes out to be 3.25 ampere. Just note it down and tell me if you have any doubt. Rania, you don't have class on Tuesday. It's class 12 batch. Okay. So charge can be have point. I didn't get your question, Fatma.
No, I meant that sir, charge has to be whole, right?
Charge has
Like point. It's no. I'm asking if charge can have a point.
charge can have point.
0.5.
Fatma, charge is a property of matter, right? This charge is over material thing. Like if you have a sphere, then a sphere could have charge. If you have a proton, this proton have a property which is known as charge. So I literally didn't get your question. A charge can have a point. You want to say that at 5 seconds can I have a charge? Do you mean point means time?
No, sir. Like it's 32.5, right?
Oh,
Does it have to be whole?
no. That's fine. That's 32.5 coulomb. Okay, that decimal. Okay. So you're saying about quantization of charge, right?
Yes.
That should be in whole number. That should be whole number multiple of E. The charge could be 1.6 coulomb. It should be multiple of E. Like it should be multiple of 1.6 into 10 raised to the power minus 19. So there's decimals can be in their charge. But when we deal with microscopic charge, like charge of 32.5 coulomb is a huge charge. At this level, we simply ignore quantization. Otherwise, in principle, you are correct that whatever charge you have, that should satisfy the quantization condition. Quantization condition says your charge should be an integral multiple of E. So it should be an integral multiple of E. Means on dividing this with E, you should get a number, a real number. But when we deal with macroscopic charges, like this 32.5 coulomb is a big charge, macroscopic charge. When you deal with macroscopic charges, then you will simply ignore quantization.
Okay, sir.
Let's erase it. The next question is, so that was about current. Let's start with drift velocity. Current in metallic conductor. Current in metallic conductor. Or I can just write it as current in metals. See, whenever you have a metal, in a metal, current flows due to motion of free electrons. So in this topic, it's a big topic. It covers a big portion of your current electricity, that current in metal conductors and metals. In this topic, we will see at electronic level how current flows in a metal at the level of an electron. So your current electricity in your syllabus is in two parts. One is theoretical, which is related to this drift velocity. Another is circuit analysis, a major portion of which you have already done in your capacitor chapter number 2. So in current in metals, so you have a conductor, a metal conductor. Now, as discussed in chapter number 2, conductor have ions, immobile ions. Ions cannot move. If you take a conductor of copper, then that conductor will have Cu2 plus ions. And these ions are immobile. They cannot move. These are immobile ions. These are immobile ions. And along with these immobile ions, there are plenty of free electrons. Conductor have plenty of free electrons. Plenty of free electrons. These electrons are moving with various velocities. This is V1. This, or I should write this as U1. U2. U1. So this is your conductor. At electronic level, when you have not applied any voltage, any cell, any battery to this conductor. So all electrons are in motion due to thermal velocities. U1. So these are free electrons. So U1, U2, UN are thermal velocities of electrons. Thermal velocities of electrons. These are the velocities of electrons due to heat energy. If you take a conductor, if you place that conductor in a room, then at room temperature, that room has sufficient energy, sufficient heat energy. That heat energy will move these electrons. That heat energy is responsible for the velocity of these electrons. That's why we call these velocities as thermal energies. So Giovanna, if all these electrons are moving, so what do you think? Is there current in the conductor? Does this conductor have current? Jubana,
No.
why not? Because current is flow of charge. All charge particles are moving. There should be current. Yes, Jubana. Yes or no? Still no?
No. Yes. Yes, sir.
What yes? So it's current now or no current?
Current. But then, sir, when these electrons are, all these things are moving, there is a, like, they bombard each other, right? So how
So there should be current or not? That's my question.
there should be current?
There should be a current. See, understand what you're saying. You're saying that if I take a piece of wire, if I take a piece of copper, I have not connected it to any power supply. Still, there will be a current in copper wire. This is what you're saying.
No, there won't be.
Actually, if I look at individual electron, then you are correct. Correct. There should be current. If you look this at the level of individual electron, then yes, there is current. There is current because current is flow of charge. Electrons are moving, that means there is charge, current. But the net movement of all the electrons is zero. That means from this end 1 to the end 2 of conductor, there is no net movement of charge. No net movement means if one electron moves from end 1 to end 2, at the same moment, another electron will move from 2 to 1. The net movement of the charge is zero, that means net current is zero. It's something like a current of 2 ampere flows in this direction. At the same instant, in the same system, a 2 ampere current flows in opposite direction. How much is total current now?
0.
Zero. They cancel out each other. This is what's happening in this wire. Each and every electron generates some current. But due to the motion of electrons, those currents gets cancelled out. So instead of saying that currents cancel out, we say there is no net movement of electrons. No net movement of electrons means there is no net movement of electrons across the ends of conductor. There is no net movement of electrons across the ends of conductor. Or you can say that average thermal velocity is zero. Velocity is zero. There is no current, there is no net movement of electron. You can say there is not, the average thermal velocity is zero. This is how we calculate average velocity. Your average velocity is u1 plus u2 up to un divided by n. This average thermal velocity comes out to be zero. This is the average velocity of electron. The average thermal velocity is zero. So this happens if electrons moves randomly, they just collide with each other, the net movement is zero. Now, I connected this conductor, okay, I will need more space, just note it down, I will rub it up. Rosa and Fatma, just let me know when you have written. Sorry. So now let's connect this conductor with a cell. As soon as I connect this conductor with the cell, this end which is connected to positive terminal of the battery gets positively charged and it gets negatively charged. Due to this positive and negative charge, an electric field gets established inside the conductor. An electric field gets established inside the conductor. This is the electric field inside the conductor. Electric field E. This is the electric field inside the conductor. This field is generated by this positive and negative charge. Now, if you remember, we have done that net field inside a conductor is 0. In electrostatics of conductor, we have done that net field inside a conductor is 0. But now I'm generating a field inside the conductor. So see, this field is basically due to this cell. If I remove this cell, then conductor will make this field to 0. This is the cell which is maintaining a non-zero field even inside the conductor. I'm repeating it again. If I remove this cell, this field comes out to be 0. Conductor will reduce this field to 0. But due to this cell, you can generate a uniform, pretty uniform field within the conductor. This field will push every electron. We have done that force on a charged particle and electric field is QE. So this field will push each electron in a direction opposite to that of motion of conductor. Opposite to that of electric field. Each of this electron will experience a force Fe in a direction opposite to that of E. So electric field will exert force on each electron. So this electric field will exert force on each electron. So the force is minus of EE. That's my second equation. If I consider the mass of the electron as ME, if mass of each electron is ME, mass of each of the individual electron is ME. So you can write that acceleration A, acceleration of electron, is force by mass of electron is minus of EE by mass of electron. That's my third equation. See, in this equation, this E is electronic charge which is constant. E, electric field is uniform, mass is constant. You can say that acceleration is uniform. You can say this is a uniform acceleration. So this is like a uniformly accelerated motion that you must have done in class 11. So you have an electron, say this is your electron. I consider this one, see. This electron has some initial velocity which is u1. Or say I'm taking some other electron which have, this is my first electron. This have initial velocity u here, u1 here. Electric force will act in this direction. Due to this electric force, this electron will start moving in the left hand side. When this electron starts moving, there are plenty of ions inside the conductor. This electron will collide with the ion and comes to rest. Then it will move again. Then again it will collide with the ion and comes to rest. So electron will gain velocity during the time it takes in two successive collisions. I'm repeating it again. So if you consider this electron will experience force due to electric field. Due to this force, this electron will gain some net velocity in the left-hand side direction. But this electron cannot move continuously. The reason is there are plenty of ions, and the size of ions is very large. These electrons will collide with the ions. One electron collides with the ions, it comes to rest. Then again, electric field will pull it, sorry. Then it will collide with the another ion and comes to rest. So this electron is moving through successive collision. It moves, it collides with ion, then it moves, it collides with another ion, then it moves, it collides with another ion. So electron is gaining velocity only for the time interval which it takes, the time it takes between two successive collisions. Let tau 1, tau 2, tau n be the time electron takes to collide with successive ions. So the time which electrons takes to collide with two successive ions is known as relaxation time. Is tau 1, tau 2 and tau 1. Is these time intervals clear? Fatma, Jabana, Froza, are these time intervals clear?
So can you explain once again?
So if I consider the first electron, see, this electron have some thermal velocity u1 in the right hand side direction. You have applied an electric field. That electric field exerts some force over the electron. Due to this force of electric field, this electron will move towards the positive end of the conductor. But while moving towards the positive end, it will collide with the ions. Because in a conductor, you have plenty of ions. The size of ions is very large as compared to electrons. So whenever these electrons move, they will definitely collide with the ions. Is it clear up to this point that this collision?
Yes.
So whatever velocity electron have gained, electron will lose once it collides with the ions. So electron will gain velocity only for the time that it takes in collision with the ions. So this electron collides with the ions and it comes to rest. Then again, electric field will exert force on the electron. Then this electron will move and collide with another ion. So the time between this first collision and this second collision of an electron is represented by tau. This is tau, the time between two collisions. Is it clear now? No.
Yes, sir.
So what was the initial velocity of first electron, Fatma?
U1.
U1. And what's the acceleration?
A.
Okay. So can you calculate the velocity of electron after time t1, tau 1? After time tau. Can I write this as V1 is its U1 plus A tau 1? Right?
Yes.
If acceleration is constant, you can use this uniformly accelerated motion. This was in class 9th and class 11 syllabus, V is U plus AT. So I'm using the same expression. U is thermal velocity initial, which is U1. A is acceleration, and instead of time, we are using tau. Clear?
Yes, sir.
Okay, just note it. I need more space for the next calculations. Afroza, Jabana. Okay, the next is after V1, we can calculate V2. So, Jabana, how would you calculate V2? Yes.
U plus
Sorry.
U2 plus A into tau 2.
Right.
Tau.
A2 tau. Right. So you can write that your V2 is velocity of second electron after time tau. After time tau 2. So after tau 2 time, you can write this V2 as V2 is U plus A tau 2. That's equation number 4, right? Or 4 or 5? What's the equation number? 5.
5.
Similarly, for nth electron, Vn is, it's U2, Un plus A tau n. That's 6. So each and every electron is moving with a different velocity. But when we observe current, we observe the average one. We don't observe individual current of each electron. We observe the average current. So we will take the average velocity. So average velocity of electrons V average is V1 plus V2 up to Vn divided by n. I can substitute the values of V1, V2, Vn here. I can write V average as V1, which is U1 plus A tau 1, V2, U2 plus A tau 2, Vn, Un plus A tau n divided by n. So V average is, it's U1 plus U2 up to Un. I'm just writing this as U1 plus U2 up to Un by n. I'm writing it as two different terms. Plus A, I'm taking this A as common, or A tau 1, A tau 2 up to A tau n divided by n. Is it clear? I just divide the whole thing into two different functions. One is in terms of U1, U2, Un, and another is A tau 1, A tau 2, A tau. Is it clear? What is this term, Afroza? U1 plus U2 plus Un. Can I write this as something? Afroza. What is U1 plus U2 up to Un by n? How much is this quantity?
This is total U.
Total U. Nah. Fatma, how much is U1 plus
Total
U2?
energy.
Nah, not even total. This is average thermal velocity, which was 0. Equation number 1. Average thermal velocity, equation number 1. So V average. Afroza, is it clear? Why is it 0? So the first equation, like average thermal velocity is 0. So it's A tau 1 plus tau 2 up to tau n by n. This is equation number 7. Now again, I don't have much space. Note it down. Afroza, is it clear why this term is 0? You just note it down and tell me when you have written. Afroza, can I raise it? Now this tau 1 plus tau 2 up to tau n by n. So what was tau 1, Afroza? What was tau 1 and tau 2 and tau n? Afroza?
U plus A into tau.
I'm just asking, what do you physically mean by tau 1, tau 2 and tau n? What was tau in this equation? What does physically tau represent? It was related to some time, huh? Rosa.
Thermal velocity.
Tau. This one, this tau. Just check the previous section. It was velocity or it was time? Just check the previous one.
Time.
Or what time? Which time?
Thermal time.
Not thermal time. This tau 1 represents the time taken by electrons to collide with the ions. Right?
Yeah.
The electron is moving inside a conductor, it's continuously colliding with the ions. So the time taken by the first electron to collide for collision with two successive ions is tau 1. What is tau 2, Afroza? Yes, Afroza, what is tau 2 here? Not formula, the same thing. What does physically tau 2 represents here? Time taken by second electron to collide with two successive ions, right? Similarly, tau n. But when I write tau 1 plus tau 2 plus tau n by n, that I'm taking average time in two successive collisions. Here, tau is the average time taken by electrons for two successive collisions with ions. For two successive collision with ions. Known as relaxation time. See, this relaxation time simply means, see the first electron, let's first electron take 1.2 milliseconds. Second electron took 1.3 milliseconds. Fourth electron took 1.4 milliseconds. When we report current or we report average velocity, we don't consider motion of individual electron. We rather consider the average motion. So we don't report relaxation type of individual electron. We rather report the average relaxation type. That is 1.2 plus 1.3 plus 1.4 divided by 3. That's what I'm doing. Tau 1 is the time taken by first electron in 2 collisions with the ions. Tau 2 is the time taken by second electron for 2 collisions with the ions. Similarly, is tau 1 for nth electron. But tau is the average for the conductor. Like tau 1 is this, tau 2 this, tau 4 this, and tau comes out to be 1.268, So I would say that on an average, all electrons inside this conductor collide with 2 ions in time 1.256. So that's on an average. So this is the relaxation time. I call, what is the equation number?
8.
8.
So let's substitute 8 in 7th. If I substitute 8 in 7th, then the average velocity comes out to be, it's acceleration A multiplied by tau. This is equation number 9. I have calculated acceleration in equation number 3 or in equation number 4. A is minus E by m. That was 3 or 4?
3.
3. Let's substitute equation number 3 in 9. If I substitute 3 in 9, that means your average velocity is minus of E tau by m. This negative sign just represents that direction of average velocity exactly opposite to that of field. This negative sign shows that direction of average velocity is opposite to that of field. To that of electric field. If I just consider the magnitude of average Coulomb velocity, just magnitude of V average, then I will simply write this as V average. Negative sign represent direction. I'm not considering negative sign, so it's E tau by m. This is the magnitude of average velocity. So this is the average velocity with which electrons move inside a conductor when you connect it through a cell or a battery. This is the average velocity. Is it clear? Whenever you connected a conductor like a copper wire with a cell or a battery, the average velocity with which electrons travel in that wire or conductor is known as V average.
Sir, ME is the mass, right?
ME is the mass of electron, right?
Okay.
Electronic mass, not the mass of conductor, electronic. Can I erase it? So this average velocity with which electrons drift towards the positive end of conductor So I'm not writing that electrons are moving. I'm writing electrons are drifting. The reason is the motion of electron is not continuous, not a free motion. It keeps on colliding with the ions. So it's not moving in a straight line or continuous motion. It keeps on colliding and then moving. So it looks like electron is drifting towards the positive end of conductor. Is known as drift velocity. Is known as drift velocity. So drift velocity Vd is basically E tau by. So this is how you can calculate drift velocity. So drift velocity is the velocity with which electrons in a conductor move. But when you have applied the cell or you have connected this conductor to the cell or battery. Is it clear?
Yes.
Okay, if I don't apply the cell, what's the average velocity, Afroza? If I didn't connect this conductor with the cell, then what would be the average velocity of electrons? Afroza, if I don't connect this conductor through the cell, then what would be the average velocity of electrons? Giovanna, what would be the average velocity if I don't connect this with the cell or battery?
0.
0. That would be average thermal velocity. It could be 0. Now, there are few conceptual questions on the same concept. Just remember one result. On increasing temperature, as we increase temperature, relaxation time decreases. Relaxation time decreases. See, what was relaxation time? Relaxation time was the time taken by electrons in two successive collisions. So that's time taken by the electron in two successive collisions is known as relaxation time. If I increase the temperature, then thermal energy will increase. Due to thermal energy, electrons will collide more frequently. Electrons collide more frequently, that means time will decrease. So if I increase temperature, then relaxation time will decrease. And through this expression, your drift velocity will decrease. Similarly, if I decrease temperature, then relaxation time will increase. That means your drift velocity will increase. Drift velocity is directly proportional to relaxation time. That means on increasing temperature, relaxation, or I can say that drift velocity increases. Drift velocity decreases, and vice versa. Okay, just note it down and tell me if you have any doubt. Okay. After drift velocity, let's calculate relation between drift velocity and current. To see how this drift velocity is related to current. Relation between current and drift velocity. Okay, just tell me a very simple question. It's not a numerical, it's just a simple calculation to check how well you understand the concept of drift velocity. Let's say I take a conductor. I say the length of the conductor is 10 meter. And for this, I need answer of each one of you. Just calculate and report your answer in length. Test room, chat room. The length of the total conductor is 10 meter. Length of conductor is 10 meter. Drift velocity is 10 meter. Let's say drift velocity is 10 raised to the power minus 2 meter per second. Calculate time taken by electron to move from one end to another. To move from one end to another. Solve this question and report your answer in chat room. No one calculated it. Huh? See, the simple formula that you can use here is speed is distance upon time. The speed with which electron is moving is this 10 raised to the power minus 2. The distance that it will cover is 10. Now calculate time, Fatima and Afroza. Jubena got some answer. Though Jubena is making some calculation mistakes. It's simple. Speed, distance is speed. Speed is distance by time. Na? So the distance that electron will cover is equal to length of the wire. The velocity is 10 raised to power minus 2. No answers. Fatima and Afroza, if you can't calculate, just tell me. Okay. 0.15. 1. Why 1? See, time, speed is distance upon time. So time comes out to be distance upon speed. So distance is 10 meter and speed is 10 raised to the power minus 2. If I take it in the numerator, then it's 10 into 10 raised to the power plus 2. It comes out to be 1000 seconds. Fatma, why we were getting 1?
Sir, I didn't consider the power.
You didn't consider.
Minus 2.
Afroza, you? You as ever making some calculation mistakes, huh? Anyways, is it clear for every one of you, each one of you?
Yes, sir.
Now you get what is different drift velocity. Drift velocity is simple velocity with which electron is moving inside a conductor. That's the simple drift velocity. After drift velocity, there is one important calculation, that is relation between current and drift velocity. Relation between current and drift velocity. So see, current and drift velocity should be related. Because what is current? Current is flow of charge. And drift velocity is the velocity with which charges move. So there should be a relation between current and drift velocity. What do people think? That relation should be direct or inverse? Current should be directly proportional to drift velocity or should be inversely?
Direct.
Direct. Okay, yes. So relation between current and drift velocity. So let's take a conductor. Let's take a conductor. The area of cross section of the conductor is A. The length of the conductor is L. So A is area of cross section. A is area of cross section. And L is the length of conductor. I connected this conductor to a cell. Current I is flowing through it. This is the direction of current. I'm considering one more quantity which is small n. Small n here is number density. Number density means number of electrons per unit volume. Number of electrons per unit volume. And Vd is drift velocity. Now, I will not solve this derivation. You people will do it. This is drift velocity. Okay, let's start with the first one, Afroza. Let's start with Afroza. Afroza, what is the volume of conductor? What is the volume of conductor, Afroza? Area of cross section is A and length is L. Afroza, how much is the volume?
A into L.
A into L. Very good. This is the volume of conductor. That's first equation. Fatma, if number density, number of electrons per unit volume is small n, then how much is total number of electrons? Fatma, how much are the total number of electrons in the conductor? See, the total volume is this and number of electrons per unit volume is this. How much is total number of electrons?
A into L into N.
Yeah, it's basically total volume into number of electrons per unit volume. So it's AL multiplied by N. That is equation number 3. Charge on an electron is E. Charge on an electron is E. So Jovana, how much is the total charge in conductor? Jovana, how much is the total charge? You're not audible. Charge on one electron is E and that's the total number of electron. What is the total charge? Total is Ne.
Okay.
I can substitute the value of N from 2 in 3. If I substitute 2 in 3, it comes out to be delta Q is ALNT. That's equation number 4. Now, Afroza, again, on you again. So if the drift velocity is Vd and the length of the conductor is L, I need time taken by electrons to travel length L of conductor. What would be the time, Afroza? I'm moving in sequence, each question for each one of you. Yes, Afroza, how much is the time taken by electron to travel L length of conductor? In terms of these parameters, these 4 parameters. No idea. Okay, Fatma, will you try?
Distance by time. L by
Yes.
distance.
Drift velocity is length by time. So time will be length divided by drift velocity. This is equation number 5. Okay, Jubena, how would you calculate current? You have charge, you have time. How would you calculate current through conductor?
I equal to
Yeah,
QT.
I equal to delta Q over
Delta.
I call this as equation number 6. So I can substitute 4 and 5 and 6. Okay, just substitute 4 and 5 and 6 and get the value of current. Do it now. And as expected, the current should be proportional to drift velocity. Do it now. Answers. Answers. No, that's straightforward. Yes, Fatima, you're correct. Yeah, Froza. Froza, this delta T will cancel delta T, right? So I comes out to be delta Q, which is ALNE divided by L over VD. L will cancel this in, this VD will come to numerator, and it comes out to be NEAVD. So as expected, current and drift velocity are directly proportional to each other. So I is NEAVD. So can I raise it? Okay, after this current and drift velocity, the next is Ohm's law. So Ohm's law says if you have a conductor, the voltage drop across the conductor is V, and the current flowing through a conductor is I. So Ohm's law says the statement is if current flowing through a conductor is directly proportional to the voltage applied across the ends of conductor. So that's Ohm's law. The current which is flowing through a conductor is directly proportional to the voltage applied across the ends of conductor, provided physical conditions like temperature, and pressure remain constant. So it says V is proportional to I. The current flowing through a conductor is directly proportional to the voltage applied across its end. If you remove the sign of proportionality, we use a constant R. This R is known as resistance. So you can say that resistance is V by I. So if I draw a graph between V and I, we'll draw two graphs. If I draw a graph between V and I, This is voltage, this is current. This is voltage and this is current. This angle is theta. If I take slope of this graph, V versus I graph, if I consider slope of this graph, slope is tan theta, which comes out to be voltage by current, so it's V by I. And what is V by I? Voltage by current is resistance, so slope comes out to be equal to R. If I take slope of this graph, so on x-axis, let's take V, on y-axis, it's current. It's voltage on x-axis and current on y-axis. So, Afroza, what is the slope of this graph? This is theta. Afroza, what?
Sin theta.
Yeah, then in terms of current and voltage, it would be? Yes, what? Afroza, in terms of current and voltage, this would be?
I by V.
I by V, very good. And what is I by V? Is it R or 1 by R?
1 by R.
1 by R. So remember, if you have V versus I graph in this way, then V by I is R. The slope is R. But if you have I versus V graph, then the slope will be 1 by R. So just note it down, Ohm's law. Sure. Fatman or Froza, can I raise it? Yes, Afroza, can I raise it? Okay, I'm erasing it. So Ohm's law means V versus I graph is a straight line. Let's see some detail of Ohm's law. Ohm's law means V versus I graph is a straight line. Straight line. This is the meaning of Ohm's law. You can understand Ohm's law in one more way. Ohm's law means at a constant temperature, resistance does not change with voltage. Resistance does not change with voltage. This is again the meaning of Ohm's law. That at a constant temperature, resistance does not change with voltage. That means, say if you have a voltage of 10 volt, and if I say that current is, say it's 10 ampere, your resistance is V by I, which is 10 by 10, it's 1 ohm. If this system is following Ohm's law, if I change your voltage instead of 10, if I say my voltage is 8 volt, if this system is following Ohm's law, that current will shift it to 8 ampere. So that resistance will remain 1 ohm. This is physically the Ohm's law. That on changing voltage and on changing current, your resistance will not change. If it does not change, that will mean that your system is following Ohm's law. It's obeying Ohm's law. Just note it down, then we'll do the next topic. Next thing. Let me know when you have written, I will rub it. Sorry. Fatma, Jubaina, Froza, can I erase it? Froza. Okay. The next is a definition of ohmic and non-ohmic material. And non-ohmic material. So ohmic are those material which obeys Ohm's law. So ohmic material means material which obey Ohm's law. V versus I graph is a straight line. V versus I graph is a straight line. These type of materials are known as ohmic material. Examples. Example of ohmic material. The first example is like conductors. Conductors are ohmic. V versus I graph will be a straight line. Carbon resistors, another example of ohmic material. Here again, V versus I graph is a straight line. This is V, this is I, this is straight line. That's ohmic material. After ohmic, you have non-ohmic material. You have material which are non-ohmic. In non-ohmic material, these are material which don't obey Ohm's law. Material which don't obey Ohm's law. V versus I graph is not a straight line. Is not a straight line. Examples. Diodes, transistor. These are some examples of materials which are non-ohmic. For non-ohmic material, your graph will not be a straight line. Say, if I take a particular non-ohmic material, then your graph won't be a straight line. The graph will look like this. You can have these type of graphs if you have non-ohmic material. So always remember this definition. Ohmic means material which follow Ohm's law. Non-ohmic means material which don't follow Ohm's law. Following Ohm's law means V versus I graph in a straight line, but for non-ohmic, your V versus I graph will not be a straight line. Okay, just note it down. We'll do some more examples. Can I raise it? It's diode basically. Diodes, you must have seen diodes, the normal LED lights that you use in your home, LED lights. Those LED lights are basically diodes. If you're in a TV remote, the TV remote had a bulb at the front end. Even the AC remote have a bulb at the front end. That bulb is basically a diode. Transistor, you may have not seen transistor, but diode you have seen. Your LED lights are basically diodes. The bulb at the front end of your AC is basically a diode. So diodes are non-ohmic material. They don't obey Ohm's law. Here V versus I graph will not be a straight line. So can I erase it? Okay. Next thing. The next thing is resistance. Afroza, you have written it? Afroza, can I erase it?
Yes,
After this, the next is resistance. So the resistance is the obstruction offered by material. Resistance is obstruction offered by material in flow of current. So the obstruction that the material offer in the flow of current is known as resistance. That's the resistance. It is the we have done drift velocity. In drift velocity, did you observe something which oppose the flow of current, something which obstruct the flow of electrons? During drift velocity, we came across some systems, some particles which basically obstruct the flow of electrons. Yes, that was ions. So the collision of electrons with ions is basically resistance. Flow of electron is current. That collision of electrons with ions is opposing the flow of electrons. So that collision of electron with ions is basically resistance. That is the cause of resistance in your system. It is due to collision of electrons and ions. That's resistance. You can write your resistance as the ratio of V by I. It's a scalar, simply a scalar quantity. Its SI unit is ohm. We can even calculate your resistance in microscopic form. Resistance in microscopic form. You can easily calculate your resistance in microscopic form. So in microscopic form, the resistance is, so the expression of current in a conductor, microscopic form means you have to calculate resistance in terms of relaxation time, number density and all. So let's take a conductor. The length of the conductor is L. The area of cross section is A. I connected this conductor through a cell of voltage V. Current through the conductor. Current in conductor. Okay, Afroza, let's start this derivation with you. The expression of current is I is NEAVT. That's first equation. Afroza, what is the expression of drift velocity in terms of electric field and relaxation time? Afroza, drift velocity.
E tau by
Yeah, E tau by M, right?
yeah.
Like substitute 2 in 1. I get I is NEA VD. VD is EE tau by M. So current comes out to be it's NE square A tau by ME. That's equation number 3. Okay, Fatma, did you remember any relation between electric field and potential difference? Fatma, do you remember any relation between potential difference and electric field? No.
No, sir.
No, okay.
No.
Giovanna, you? Did you remember relation between field and potential?
Is it PE cos theta, that one?
Not that one. This was gradient of potential. Electric field is delta V over delta R. Remember, this we have used even in capacitors. Electric field is potential difference by separation. Here potential difference is V and separation is L. So you can write your V as EL. This is equation number 4. Okay, I don't have much space. Just note it down. Just note it down. Okay, if I substitute 4 in 3, not 4 in 3, I need E, sorry. This is 4. Substitute 4 in 3. If I substitute this equation number 4 in 3, then I would get I is NE square A tau by M into. So instead of E, I'm writing V by L. So if I cross multiply it, it's ML by NE square A tau is V by I. This V by I is R. So R is its ML by AN E square tau. So this is your resistance in terms of microscopic quantity. So resistance depends upon number density, it depends upon relaxation time. Okay, just note it down. Okay. Okay, let's stop here. Okay, there's one more announcement. From today onwards, I'm sharing 3 to 4 questions or 4 to 5 questions daily after each class. Those 5 questions are your assignment. I need that assignment to be submitted within 24 hours. So from today onwards, you will submit assignments. I'm sending 4 to 5 questions in group after each class. Though I'm sending solutions, but try not to use solution unless you have tried a question for at least 2 or 3 times. So don't just copy the solution. I'm sending the solution just for the reference. So from today onwards, I need your assignment. Just scan your assignment and text it to me. You can text it to me or to the ORCID number. To the number through which you will get the assignment, you can WhatsApp your assignment to that number. It would be better if you WhatsApp your assignment to that particular number. Okay, let's stop here. We'll continue on Wednesday. So, okay, love is. If you have any doubt, we can discuss.